Okay, let's continue on with our examples on naming our alkenes and alkynes. I'm noticing that on the video here, this drawing's a little bit small, so let's see if this works. Maybe it will. All right, so there we go. We can take a look at this first one. What we have to do is establish the root. As we establish the root, we look for the longest continuous chain, which is pretty easy. 1, 2, 3, 4, 5, as it's just a straight chain. So this is pent. You can see the presence of a triple bond. So it is pentyne. Now we just have to number it so that this triple bond it gets the lowest possible number. From the left, it exists on carbon 2. From the right, it exists on carbon 3. So we should number it from the left. And it is pent2-ine. Okay. Here's another one. You can see that we have 3 carbon chain. So that is prop. I can see a double bond. So it's propene. And it is on carbon 1. Okay. So since there is only one place to put this double bond, that would give us carbon 1, because if I move the double bond over here, I'd have to number it from the left. So while this is technically prop1-ene, because there are no isomers of where the double bond can be, the 1 is often dropped, and you will see that reflected in your examples in the textbook and online. So we would actually call this propene. So it is a situation in which we drop the number, okay? We do this in chemistry. We try and drop redundant numbers whenever possible. And so in this case, because I cannot put the double bond anywhere else without changing the number, like for example, if I do this, whoops, knew this was going to cause me problems, versus this, all right, I would just number this one from the left, prop1-ene. I would number this one from the right, prop1-ene. So the 1 becomes redundant, and we just call it propene. All right, on the next one here, you can see 2 double bonds in a 1, 2, 3, 4 carbon chain. So this is but-diene. Okay, because we have 2 double bonds, we have 2 of the alkene functional groups. We just have to put in the numbers, and so when you take a look at it, numbered from the left or the right, we can see that there's a double bond at carbon 1 and carbon 3. So this is but-1,3-diene. One more to look at here. I'm trying to zoom in, and this is awkward. 1, 2, 3, 4, 1, 2, 3, 4, and 1, 2, 3. Okay, my longest continuous chain must be this one because it is the group of 4 that contains the double bond. So it's another butene molecule. I'll have to put the name up top, I think. So this is but, and it is going to have an ene suffix. There's a couple of different places I could put the double bond to change the numbers, so I must use the number here. Okay, and so this is but1-ene, and then we have this methyl group hanging out here at carbon 2. So there's your 2 methyl but1-ene. All right, so there we go. That's more naming practice there. Now I've got some line angle formulas for you. I think what we'll do is we'll just name these. We can also come up with the empirical formula if you wish, but the space is kind of limited here. I didn't space this one out very well. So let's race through these ones here. This is carbon 1, 2, 3, 4, 5, 6, 7, 8. So I have an octene molecule here because I can see the double bond. I just need to figure out what's the lowest number. 1, 2, 3, 4. So an oct4-ene from the right. 1, 2, 3, 4, oct4-ene from the left. So it doesn't really matter, and this one just gets known as oct4-ene. Okay, Here's one, looks like an arrow. It's not, it is an alkyne. So let's figure this one out. 1, 2, 3, 4, 5, or 1, 2, 3, 4, 5 going down towards the bottom part of the arrow here. Any change in a straight line with double or triple bonds saves the need for a zigzag. Okay, and so we have 1 to 1 here, then we see a change in bond, and then another single, and another single. So if I go with the top, this is 1, 2, 3, 4, 5. It is a pentyne molecule with a branch here, and we need to number this pentyne so that the triple bond has the lowest numbering. It's either 3 from the right or 2 from the left, so this becomes pent 2 yne, and now we just need to add in our methyl group, which now, because of our new numbering strategy, has to be on carbon 4. So we have 4-methyl pent 2 yne for this one. Okay, very similar idea between this example and the next one that you see. I've thrown the other part on this, or equivalent part on the other side, making it look like a TIE fighter. Yay, Star Wars. And we just have to count this one out. So there's 1, 2, 3, 4, 5, 6. You can see that there's going to be a whole bunch of different 6s. It really doesn't matter which way we go with this one. So if we go this way, if you like, okay, 1, 2, 3, 4, 5, 6. This is a hex molecule. You can see that it's a hexyne with the carbon, the triple bond right in the middle at 1, 2, 3, regardless of the way we go. So we have hex 3 yne, and now we just have 1, 2 methyl branches to take care of, and so this is 1, 2, 5. So we have 2, 5 dimethyl hex 3 yne. I know it just rolls off the tongue so easily there. But yeah, we have 2 methyl groups, so we use prefix di there. We include the numbers for where they are, and we now have the number in our suffix for the presence of where the triple bond might be, because there are other positions in which it could have existed. Okay, I have another one here for you. This one's a fun one. It looks like a puppy, but maybe you see it. I know I do. We just need to figure out longest carbon chain. And so 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4. So it looks like we have a couple of choices. We can go from the nose down to the hind leg, or the nose up to the end of the tail. So if we go from the nose to the tail, all right, that's our longest continuous chain of 1, 2, 3, 4, 5. There's a double bond in it, so it's a pentyne, and you can see that the double bond would be lowest numbered from the right. So this becomes a pent 2 ene root and suffix. We just then have the dimethyl group here at carbons 3 and 4. 1, 2, 3, 4. And so this is similar to the one we just did. 3, 4. Dimethyl pent 2 ene. All right, similar looking one again, not a puppy, maybe a giraffe, you tell me. And so again, we look for the longest continuous chain that contains the double bond. It's pretty easy to see that it's got to go from here. 1, 2, 3, 4, 5, 6. 4, 5, 6. Sorry, 1, 2, 3, 4, 5, 6, 7. 6, 7. So again, we can follow from the nose of the giraffe all the way to its tail, and that ends up being 7 carbons long. And so we have our heptene molecule, and you can see that the double bond would make sense at carbon 1 right here. So you have a hept 1 ene as your root and suffix, and then we have similar branches like we did with the puppy, and so it's another dimethyl hept 1 ene. And so we just need to put in the numbers, and they would be at 1, 2, 3, 4, 5, and 6. Okay, so there you go. That's your 5,6-dimethylhept-1-ene. One more to quickly do here, and for this one, you can see that we have a kite, or something like that, but I see a cyclic structure here. Okay, so 1, 2, 3, 4 carbons in the cyclic structure, so this is a cyclobute butene molecule. Now, because this is the most influential thing in a cyclic structure, it's got to be at carbon 1. All right, so now we're just trying to figure out what would be the number of this branch. If I go here, 1, 2, 3, 4, I've kind of omitted or eliminated my double bond. That doesn't seem right. So maybe it's 1, 2, 3, 4 this way, because then I've used and gone through the double bond in my counting. Or it's 1, 2, 3 if I go counterclockwise. 3 is lower than 4, and so I have a 3-methyl cyclobutene. If you put cyclobute-1-ene, I would not mark it wrong. It's just highly unlikely that you'll see it if there's only one double bond in a cyclic structure, because it's always going to be carbon 1. Okay, kind of ran myself out of time on this one, going through that many examples. So in the last video for this lesson, I will take you through the various diagnostic tests.